So this concept that the area underneath the velocity function represents the displacement is a key idea in math and calculus and also in physics. So this is something we use in physics. Okay, so what we want to do then is find when we have a velocity function. So here's my velocity function here. So I'm going to plot it. So 0, 0, I have a point. Okay, 0, 0. At 1 second, I'm at 2 meters per second. At 2 seconds, I'm at 5 meters per second. At 3 seconds, I'm at 3 meters per second. 4 seconds, I'm at 6 meters per second. And at 5 seconds, I'm at 6 meters per second. So there's my velocity function. It's kind of going, you know, all over the place here. I'm going faster, faster, slower, faster, just staying at a constant speed. Look, I'm all over the place here. But what we can do is we can estimate the net displacement by calculating the area underneath this curve. Okay? And we're going to do this by using an average. Now, we don't know that this went between these 2 points in a straight line. It could have gone like that. We don't know, right? So the area would change depending on how it went between the 2 points. However, we're going to make an assumption that it went like that, and we're just going to use the average because this is going to be our best guess. Okay, so this is not calculating the exact displacement because there's no way to know what the exact displacement is based on just these discrete pieces of information here, these discrete velocities. However, if we make the assumption that it is in a straight line, we'll just use the average velocity and find the net displacement in that interval. Okay, so if I want to find the displacement of that first interval, okay, I'm going to say that, well, the average velocity is 1 meter per second for 1 second, so I've got 1 meter of displacement. Okay, in that next interval, I'm going to say that the average velocity is going to be 3.5 meters per second, okay, for that 1 second. And so in this area here, that area is going to be 3.5 meters. Okay, and if we count up the area there, yeah, the area is in fact 3.5 square units. In that next interval, I'll use a different color here for this next interval. The average velocity was, it looks like 4 meters per second, so we've got a displacement of 4 meters. In the next interval, okay, the average velocity here is going to be 4.5 meters, so that's going to go, we're going to say for 1 second we traveled at 4.5 meters per second, so that displacement there is going to be 4.5 meters. And then the last interval, this interval here, well, the velocity is constant at 6 meters per second, so we're just going to say that that interval is 6 meters. Okay, so this is a way we can figure out, we can start with a velocity function and end up with getting information about displacement, how far we've moved in those time intervals. And in fact, we can find net displacement here by just adding that all up. Okay, so my net displacement here is, let's see, 4.5, 8.5, 13, 19 meters of net displacement. So we can find the interval displacement as rectangular areas in the graph as well. So in this case here, we did use the trapezoids here, but we can easily make the assumption that the area is going to be these rectangular areas here. We just take either the highest, fastest velocity or the slowest velocity and find the rectangular areas, which would even simplify things further. However, you can see that the estimate would not be quite as good as the triangular estimate. But when we get to calculus, the as long as we have an idea that we can calculate an idea of what the displacement is, the error that our shapes are going to generate are not going to be significant, because what we're going to do is we're going to end up using smaller and smaller interval widths. So where we end up using smaller and smaller rectangles, and those smaller and thinner rectangles give us just as good of an estimate as these trapezoids do. So we'll use a simpler shape of a rectangle, and we'll end up getting our accuracy through really thin rectangles. Okay? So for now, we're just going to stick with trapezoids, and just to give us, an idea that it's actually a very good estimate to estimate the areas. But when we get into calculus, we're just going to use this idea, and we're just going to make it better by making it using narrower time intervals. Okay, and these rectangular areas are called Riemann sums. Okay, they have a special name for them. Okay, so to summarize this then, what we started with was position time. Okay, our displacement function, we find the slope, we get velocity time function. Okay, we didn't really do acceleration, but we can find the slope of that and find acceleration time function. But what we did was mainly between these ones. So here was finding slope, okay, going from velocity time to a position, we found the area. So from here to here to find velocity, we found slope. From velocity to find position, we used the area. So that's a key idea. That's a central idea when we get to calculus.